So we had basically said that with standard deviation, it can be affected by outliers, right? Because we take all the data values into calculation. And so if you have a really large data value or a really small data value, like it affected the mean, can also affect the standard deviation. So we talk about a different calculation for figuring out variation or the spread of our data. And that is where the idea of the interquartile range came in, because you're looking at quartile 3 minus quartile 1. So that's, the center, the middle 50% of your data. And in that way, you are not affected by the greatest data value and the lowest one, right? The largest and the smallest. So quartile 3 minus quartile 1 is how we would figure out what the interquartile range is going to be. So again, just some of the description. I'm trying to keep that on the same screen. So you can see here, we're defining the quartiles in that box at the bottom. So to find quartile 1, basically what I would do is take my entire data set and find the median first. So, the halfway point, right? So you have half the data below the median and half the data above the median. And then for the lower half of the data, you find the median again, which will be quartile 1. And then for the upper half of the data, you find the median again, which will of course be quartile 3. And then of course we had talked about what to do if you have odd or even number of data values. So remember, we had seen these two examples based on that. So that's kind of where we were at. And like I said, we were working on this example here. So you can see we found our range. The maximum value in this data set was 25. The minimum was 5. So of course, 25 minus 5 comes out to be 20. Let's make sure that guy is large enough for you guys to see. All right, looks like Crystal has her sound back. So for interquartile range, since we are dealing with medians, you do need to arrange your data from smallest to largest. So I actually did that after class, so we wouldn't be spending class time doing that. So you can see how we have our data laid out, and how many data values do we have? So even number.
I'm lying.
Is it not? Well, we're going from 10 to 24, so I think that's 14. An odd number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
Or 15?
Yep, 15, because you can see how we have that one space blank over here. So that's telling you we don't have the same number of data sets. So we have 15 here, so it's an odd number. So that means when we were trying to find the median, so remember, if we find the median for the entire data set, you can use the built-in function for that one. Median. Oh, look at that, it automatically selected it. Thanks. Median is 8, which actually should be this number over here. Let me get my location. So if this is my centermost location, then we should of course have 1, 2, 3, 4, 5, 6, 7 data sets above it, and then 1, 2, 3, 4, 5, 6, 7 data sets below it, right? So above and below. So of course, median, remember, also represents the second quartile. So we can say this is the median or quartile 2, right? So now that we know where the break is happening, you can basically now calculate the median again for the top half, and then calculate the median again for the bottom half, right? And so what you can do is, when you are figuring out what quartile, is this blocking your vision? Yeah. So to find out what quartile 1 is, which remember is the median of the data value below the median for the entire set, you will use the median function again, but this time you are only selecting the first half, right? So it should only be those values from 5 to basically the first 8. You can see that comes out to be 7.5. But the second one, same thing, right? Median, but this time you're doing from 8.25 till 25. So you can see what quartile 1 and quartile 3 comes to be. And then remember, interquartile range was basically where you took quartile 3 and subtracted quartile 1 from it. So 10 minus 7.5, right? Which of course comes out to be 2.5. So again, remember, in this case, we're basically saying it is not going to be affected by the outlier. And basically in this data set, which I guess, let me go ahead and clear out this writing here. In this data set, do you think we have an outlier, either a very small or a very large data value compared to the rest of the set?
45.
Yeah, I would say 25 qualifies as an outlier because that's a big gap between 15 and then all the way to 25. So I think that's a pretty big jump that we're seeing here because the others are pretty close to each other in terms of, how spread out the data is. So questions on calculating quartile 1, 2, 3, which again, quartile 2 is your median for the entire data set, and the interquartile range.
Does the median even take the outlier into account technically?
Technically, yes, because you are, well, yes and no, because median does not use the calculation, right? It's a position, but we are still saying, because you're looking at the entire data set. So like in the second half where we calculated quartile 3, the position of the median, of course, does not get affected by the outlier, but the outlier was still being used in the bottom half, right? Or the top half, I guess you would say, of the data set. So yes, in a way you are using it, but it's not affecting what the median will come out to be. Like, the mean would change because mean uses the 25 in its calculation, but median is just using how many data sets you had there. So technically, yeah, median is not being affected, which is the reason why interquartile range is not being affected, right? Because you're just looking at quartile 3 and quartile 1. So it's not affected by the outlier in that sense, because it's not actually in the calculation. And I'm just using the underscore, because I didn't want Q1, if I didn't use the underscore, to look like I'm talking about a cell notation, because how Excel does A3, C4 kind of thing. So that's why I'm using the underscore, so I'm talking about quartiles. Okay. Anybody have questions on that, either in the classroom or on Zoom? I didn't see anything on our chat here. All right, please let me know, guys, if you have a question. So the next thing we want to dive into is, okay, seems straightforward. All right, not a there. Come on, go away. The 5-number summary and box plots will be the next thing we want to talk about. So 5-number summary basically will be, and we've honestly looked at all of these values at this point. The minimum value for your data set, quartile 1, median, which again is quartile 2, quartile 3, and maximum, right? So look at the values we already have here. So if we did the 5-number summary, sure. You have the minimum value. You have quartile, that should be a 1.
When you put,
Exclamation, because I just left my shift.
I've done that.
Oh, all the time. And maximum. Now remember, quartile 2, technically, I guess I'll put a slash, can be the median for the entire data set. So we actually already have this, right? Because we already calculated the minimum here. So we know the minimum is 5. We know the maximum, again, we had already taken a look at that when we did our range. So the maximum was 25. And then we just got done doing quartile 1, which came out to be 7.5. Quartile 2 was the median for the entire set, which of course was 8. And then quartile 3 was the 10. So we actually already did all 5 of those calculations, or, identified what those values were when we calculated the range and the interquartile. So you can do the 5-number summary to start out with, and then you can say, okay, I know my range is going to be the maximum minus the minimum, and then I know my interquartile range is going to be quartile 3 minus quartile 1, right? So if you do the math there, you're actually already coming up with the 5-number summary here. Now, we do actually use the 5-number summary to come up with what we call a graphical representation, the box plot, and I will show you what that looks like. So whenever they're talking about the 5-number summary, guys, these are the 5 numbers that we are looking at. And then they're again talking about using GeoGebra, but again, we're just sticking with Excel or Google Sheets. So this is talking about, let's continue with the cost of a textbook in dollars from the previous example, and what would the 5-number summary for this look like? And so in this case, you can see the minimum a student paid for a textbook or the total cost of a textbook was $140. The maximum they paid was $460. The median is coming out to be about $307.50. And then you can see if you just look at the lower half of the data set, the quartile 1 is coming out to be $255. So that's basically between $140 and $307.50, right? Because that's where the lower half of our data set would be. So kind of halfway between those two numbers, I would say. And then the quartile 3 is coming out to be $347.50, which of course is going to be halfway between the $307.50 and the $460 for the maximum. And then, again, you can kind of see the statistics over here. They're just not showing you the entire data table in that image. But, obviously you can see they're taking all of these values and calculating the 5-number summary based on that. So this is what a box plot looks like. It literally is a box, right? So not a very inventive name. But you love boxes? There's nothing wrong with a box. So this is how we come up with a box plot. Hello. I just changed the battery. It should not be dying on me. Come on now. Do not even say that. So this is how you guys, we create a box plot. So you actually take the minimum value, and that is where this left-hand side line, sure, comes from. The maximum will give you the other end. So you can see, you're not seeing that, but this would be right where 140 would be. This is where your 460 would be. So this is where you draw the two ends of the line. And then the box is where those medians are coming into play. So quartile 1, quartile 2, quartile 3 is what creates the box. So this value here represents quartile 1, and you can see that's at 255. So this is where our 255 would be, somewhere in there. Quartile 3 was at 347.50, so 347.50 would be somewhere in there. And then our median was at 307.50, so of course that would be somewhere in here. So basically this value here represents the minimum, this is the maximum, this is quartile 1, quartile 3, and then median, or like I said, you can call it quartile 2. So that's what creates the box plot. And again, the idea is the visual representation of a box plot is helping us see again how spread out our data is, right? So if you just go from the minimum to the maximum value, it gives you an idea of just how spread out that is. And then for the interquartile range, which is where that box is coming into play in the center, it also tells you how spread out your data is. So you actually look at the length of the arms on either side of the box. If you're seeing, skew, right? So if the left-hand side is too long, then we would say there's a skew happening on the left. If the right-hand side arm is too long, we would say there's a skew happening on the right. And then even within the box itself, you would look at where is that median, that line in the center of the box, where is that? Is it again being pulled more to the right? Is it being pulled more to the left? Or is it kind of in the center, which is kind of what I would say. You can see there's a little bit of a pull to the right-hand side, but not a very big dramatic pull either, right? So that's kind of how you use the idea of because you can't really talk about the shape of a distribution here like we did with the histogram. But I think you can still get a fairly decent idea of if there's skewness or not, if it's symmetric or not, and then kind of based on that, make your decision. So let's take a look at the inclusion that they have here. Let me make this guy smaller. There we go. Oh, okay, looks like these guys are just going with the description of how they used. Oh, and I did forget, sometimes they do call it the box and whiskers plot also, because I guess the arms, they're thinking of them as whiskers. Not a name I hear very often, but they do. Some textbook will use that terminology, so just so you guys are aware. Same example over here, they're talking about the height of 12 people who identify as women and then create the 5-number summary. So again, you can see this, they use the GeoGebra application to do that. So we've got our 5-number summary. So you can see our minimum height here was 59, maximum is 72. And then quartile 1 is 62 inches, median is 65 inches, and quartile 3 is 68 inches. And okay, there we go. So I kind of like that they have a comparison between if we did it as a histogram or a box plot. And what do you kind of see in terms of the shape of your distribution here? Are we seeing symmetry? Is it skewed? What would you guys say? Looks like a key. Kind of does, yeah. But what would we say in terms of, I thought you said symmetry, right? Are we seeing symmetry, guys? Yes, no? I'm not even here, I'm physically here, but I really don't know what's going on. Somewhere in between. I am actually not seeing symmetry, mainly because the peak is kind of towards the right-hand side, yeah? So this is kind of the peak, and your tail is actually happening a little bit to the left-hand side. Now, it's not a very prominent left skewed, right? But you can kind of see we had the peak happening on the right-hand side, and there's just a little bit of that taper that's happening towards the left. If you look at the box plot, you will also see that the right-hand side arm is a little bit longer, or the whisker. The left-hand side one is a little bit smaller. And I would say the box kind of looks symmetric, right? It looks like that median line is kind of halfway through in the middle of the box over here. So just looking at that. So you do have to look at the arms, but you also have to look at in terms of the box, where is that median line? And that definitely looks more symmetric, right? For the box, but you do see a little bit of that elongated arm on the right-hand side of our box plot. All right. So this one definitely has only a single peak, I would say, in those terms. And even though they are saying this suggests that the distribution is symmetric, they're saying we can approximately show that the mean is equal to the median. So we can make the argument for symmetry, as Jessica was talking about, especially when you look at the box plot compared to the histogram. I think we see better symmetry in the box plot. And remember, that is because, again, the box plot is not affected by the outliers, right? Especially the box in the center, because that's just going from quartile 1 to quartile 3. Now, the whiskers or the arms will be affected by the outliers because we take the maximum and minimum values into consideration. Histogram, of course, takes the entire data set into consideration. So you will see a little bit of that pull, like I said, the skewness happening. But remember, in the last section, we had talked about if the mean is approximately equal to the median, that happens when you have a symmetric data set. So that's kind of what we're talking about here. And that makes sense because height of people is a approximately symmetric data set. So even if you took height of all the students on campus, right? you would see that symmetry kind of happening. And, you know, once we get into section 3.6, we'll talk a little bit more about those types of data sets.
How tall are you?
Sorry?
How tall?
Oh, I am not a tall person. Every year I go for my annual checkup, they like keep shortening me. I'm like, how am I getting shorter? Like, what's happening? Are you like taking some top off
My
of me?
brother's getting shorter.
But they tell me it's a thing as you get older, your bones just
Shrink.
compress. I was like, don't tell me science. I don't want to know science. Don't make me short. I know my mom at the end, her legs had started bowing, so I think that also happens as you're getting older, just because you're losing that calcium and that strength. I know, guys, lots of happy things to look forward to as you get older. Let me not depress you. But yeah, so I started out at 5'3". And according to my doctor, I'm not telling you how much they've shortened me. But when people ask me, I will still say 5'3". I'm not going down. I don't care what they say. You know, I'm barely even at 5'3", and then they shorten me. So yeah, that's okay.
I lied on my ID.
About your height? They won't worry about it.
They don't. They didn't
So,
even ask. They're like,
yeah.
how tall are you? I'm like 5'7".
Yeah.
I'm not. I'm 5'6".
And it's an inch.
Yeah.
All right, guys. Now you will see they're also talking about a modified box plot, and they're basically saying this one shows that the data values that are outliers with an X. So if you look at the bottom image, ooh, oh my God. Okay. Right now, I don't have control from there. Okay, let me try from here. So you can kind of see how they're marking those X's there, just to basically show where the outliers in the data set were. So they're basically saying, with a modified box plot, we can have the outliers shown with an X, but that requires a few more steps to make by hand. And this one, they're just kind of going into, you know, how you can do this with GeoGebra, but again, we're really not gonna worry about that. So they are basically saying, just as a comparison, will you let me cover some paragraph? Okay, so basically what they're saying is in the upper box plot, so the one on the top, we can basically see that elongated whisker or the arm, right? So we're basically saying this is showing us that the distribution is skewed to the right, and then they're saying the upper quarter of the data is very spread out. So, you know, that's the values after quartile 3, right? So between quartile 3 and the maximum, because that's where we're seeing that elongated arm or the whisker. And they're basically, it is natural to think that the data values are being evenly spread out in each region, but that is quite often not the case. So this is where the idea of the modified box plot comes in, because now you can see we're basically saying, what if we leave those outliers out of the modified box plot? So we mark those with X's to show that that is still part of the data set, but now you can see how different that, well, the whisker looks, right? Because I think the box is still looking pretty similar to the one on the top, but now we're not including all those outliers in there. And then from the lower box plot, we can see that there are 4 data values considered as outliers, and basically how far away from the rest of the data those values are going to be. So that would be the difference of including the outliers or not including the outliers. And then they're just kind of going into details about what a modified box plot would look like, you know, how to create one of those. So this one here is basically saying that there is a rule called the 1.5 times interquartile range, or 1.5 times IQR rule, which points to basically help us identify where the outliers might be, or which numbers in your data set might be considered as an outlier. So an outlier is a point which would be more than 1.5 multiplied into your interquartile range, 1.5 IQRs away from the center, the middle 50%, which is where the box in your box plot shows up. So we can calculate that after you calculate the IQR multiplied by 1.5. And then we're basically saying subtract that from quartile 1 to find your lower fence. and add that value to Q3 or quartile 3 to figure out what the upper fence will be. So anything that's smaller than the lower fence and anything that's larger than the upper fence would be considered an outlier. So think about our data set over here. So we have our IQR, which was 2.5 here. So what if we took 1.5 and multiplied that with IQR? So in this case, we would say, okay, 1.5 times, and then our IQR was right here. So I'm just going to click on that cell. You can see it comes out to be 3.75. And then remember what they're saying, go ahead and subtract that number from quartile 1 to find the lower fence and add that number to quartile 3 to find the upper fence. So that's what we're going to do. We are going to take, trying to see how do I want to write it. I guess 1.5 times IQR. And subtracting that. So it's going to be quartile 1 minus this number. And then quartile 3 plus this number. Okay. So quartile 1 was 7.5. From that, I am subtracting the 1.5 times IQR. Then I have quartile 3, and to that I'm adding our 1.5 times IQR. So we did not have anything smaller than 3.75 in our data set, right? Because the smallest value was 5, which is well within the lower fence. So this is what we would call the lower fence. This was the upper fence. Now, upper fence is at 1375. So technically, we actually have 2 outliers in this data set. And remember, this is still that example number 1 from section 3.4. So we were kind of talking about just 25 being in there, but based on this calculation, you can see 15 is actually also an outlier. So both of these guys are an outlier. Okay, so that's kind of where that upper fence and lower fence comes into play. So no lower fence, so we have no outliers on the lower end, but we do have 2 numbers. And you know, think about this, if we did a mean calculation, right? So that's the average. I'm not sure what numbers you're using. So average, and then select your data set. And you can see how, because of those 2 outliers, our average is being pulled towards the higher side, whereas your median was just at 8, but the mean is coming out at 9.8. And that's because of those 2 numbers, 15 and 25, that the mean is getting pulled a little bit on the higher side.
Why 1.5?
I guess 1.5 times is enough where you can be within, do I want to say symmetry? Not sure I want to use the word symmetry. But usually, most of your data sets, and kind of like we were talking about, you know, like the height of women, we were saying is one of those normally distributed. So usually you can be within 1.5 times of the lower and the upper end of the IQR. So that's a good place. Anything outside of that would be either too small or too large. So we kind of use the 1.5 as the factor of deciding if you are well within an acceptable range where you're not too far away from like the center position of your data. Okay, all right, very good. Any other questions, guys, on 5-number summary, box plots, and modified box plot? Now, as far as I remember, I believe, and you can correct me if anybody has made it to this part of the homework. I think my open math is asking you guys to read a box plot, right? Is it asking you to create one? Has anybody seen that? Yeah, because when I opened up the homework assignment, went through the homework problem just to make sure everything looked okay. And I don't remember where they asked you to actually graph a box plot. I think it was about reading it, but correct me if you do run into that and you need help with it. You can let me know.
I mean, so far,
Yeah,
it hasn't
so-
really asked you to grab anything. It's just asking you to.
Yeah, and Brooke says it's asking you to choose from multiple choice, so it's not asking you to create your own. So I think that should be okay. Then you guys should be able to look at the 5-number summary and then choose the correct value. But again, like I said, if you do get stuck on a problem and you need us to go over it, obviously don't hesitate and let me know. So we did talk about percentile, guys, so I guess we're just kind of coming back to it here officially, I guess. So remember again, median represents the 50th percentile. Or quartile 2. So 50th percentile would be for the median. So of course, 50% of the data will be below it, 50% of the data will be above it. And now, as we had talked about last time in class, when we are defining percentile, we're basically saying, if you are in the 60th percentile, so we're basically saying 60% of the values will be below it, right? Which means only 40% will be above it. Of course, your quartile 1 represents the 25th percentile. So 25% of the data values will be below it. And then quartile 3 is 75th percentile. So of course, 75% of the values will be below it. And I think we had kind of talked about this concept also, that percentiles are used when we're comparing the growth of the children to the population in general. And also in standardized exams, right? SATs, ACTs, and those kind of things. So idea is if a person scored in the 83rd percentile, so we would basically say all the people who took the, I guess we're talking SATs over here. So of all the people who took SATs, 83% of them had a score below this student who was in the 83rd percentile. Okay, so that's kind of how.
Did you take the SATs?
I did not have to. Since I came here as an undergraduate student, but I was a transfer student, not a freshman, I didn't have to do.
Did you take like ACT or ASVAB or anything?
For my graduate school, I had to do both GRE and GMAT, which is the version for grad school. It was not. It's those essay that get me. I'm okay, obviously, with the math section. But those essays and I don't even remember, it's been ages, but where you have to find similar meaning words. Yes, and I'm just like, oh my God, I don't really care. I'm gonna be a math major. Who knows what English needs to be? As you can see, I make fun of English all the time in our class. But that kicked my butt, yes, for sure. Alrighty, guys. So here we're basically just talking about taking this idea of box plots and percentiles and using that to basically compare two different populations. And that was also one of the things we had talked about with mean and standard deviation, that we use those to make more sense out of it when you are comparing two data sets. So the first example here is talking about the box plot of service times for two fast food restaurants are shown below, and they're asking us to compare the length of time to get served at the two restaurants. Which one should you go to if you are in a hurry? All right, let's click on the graph first. So you can see store 1, and this is, did they tell us what the time is? Is it minutes? I mean, it's got to make sense. Yeah, right there at the bottom. Service time is in minutes. So you can see store 1 is actually under a minute because that's 0.7 to a maximum of 6.3 minutes. And then your box, where quartile 1 to quartile 3 is between 1.8 to 2.9. And our median, of course, is at 2.3. Store 2 has a lower time because it's at 0.5, but then the maximum is taking 9.6, and your interquartile range is going from 1.1 to 5.7 with a median time of 2.1. So before we look at the description here, just in terms of service times, which one do you think would be, the better place to go to if we were in a hurry? Store 1 or store 2? So,
Oh, is it a fast food restaurant?
yeah, fast food restaurant. So what if both were, next to each other, because apparently that's a thing.
Like better.
But they're talking in terms of if you're in a hurry and time is a factor. So looking at this spread here, the two box plots, which one would we kind of be leaning towards? The store one or store two? Because the minimum time, if you look at store two, is 0.5, which is a little bit quicker than store one. The median also happens to be at 2.1, whereas store one was 2.3. But then when we kind of look at the upper end, right, the upper half, then we are seeing 9.6 compared to 6.3.
But isn't there median?
Say that again, Megan?
Their middle time is
For the store two, yeah, their median or quartile two is at 2.1, which is again, a little bit quicker than store one. So, Samuel on Zoom is saying store one because it is more consistently faster, because you can see that, store two does have that pull on the right-hand side, right? But again, it begs the question, was that one of those odd anomalies where you had one order for whatever reason ended up taking us longer, and it's stretching, we talked about outliers. So is that happening, or are we just saying, most orders, they're pretty quick, but then there are times where they're still taking that longer amount of time to get the orders done, because 9.6, that's almost 10 minutes. Do you really want to be waiting 10 minutes on a fast food restaurant? And that's when maybe other things, do you really want that food item? Do you really want that restaurant, if that's your favorite? Or like Raven was saying, that's closer to your location or whatever, are you willing to do that? But I think since we are just talking in terms of time, I think the other factors would be something we would not be looking at immediately. So they are basically saying store two has a slightly shorter median, which we did notice. But the service times are less consistent. You do have a wider spread. And then they're talking about looking at just the box. So you can see even at the 75th percentile or quartile 3 mark, you're at 5.7 versus 2.9, right? So even if you just look at the interquartile range, that's a pretty significant difference, almost double between store one and store two. So that means that 75% of the customers at store one are served within 2.9 minutes, whereas 75% of the customers at store two will take about 5.7 minutes. So in that sense, I would say, yeah, maybe, go with store one, which is kind of, Samuel, what you were saying. And then, they are saying, depends on your opinion about luck, 25% of the customers had to wait between 5.7 and 9.6 minutes. So they would be in that upper half of the data set, which I would not be happy about if I was one of those customers. Because, if I'm gonna be putting my health at risk by eating fast food, I don't really want to be standing in your driveway for 10 minutes, waiting on your food. Alrighty, guys, so that was one example, doing a comparison. Now, this one is talking about the box plots below show the 5-number summaries of birth weight in kilograms of infants with severe idiopathic respiratory distress syndrome, SIRS. The box plots are separated to show the birth weights of infants who survived, and for those that did not, what can we conclude from this? So the two comparisons are happening between survival and those who did not. And you can see the difference in birth weight here. So you can see at the minimum, and this is kilograms, guys, we are, I'm gonna have to estimate. So this is what, 1 point something? So that does not look too far off, right? When you are looking at the beginning weight here. But then when we look at the maximum value, the maximum here seems to be, what would we estimate, 2.75 maybe? 2.8, somewhere in there? And then for the upper,
What does
set,
that announce? Sorry,
say that again?
what does that announce?
What's the conversion from kilograms to ounces? So I would say this is what, approximately 2.75. This guy would be what, maybe 3.75? Where's the median weight at for both groups? What do you think this guy is approximately? And then the median for this guy?
1.6.
1.6 for this one, and then the upper group? Somewhere in there. Because it's in that first quarter-esque position, isn't it? Okay, where would quartile 1 fall for this group? So it looks like we're saying approximately. I don't know where to estimate this guy for. Maybe like 1.2 or something, and 1.1 for this guy here. 3.75 for this one, 2.75 here, 2.3 for this guy, 1.6 here. What do you think is the minimum, quartile 1 and quartile 3 for the set on the top? These two numbers here, what would you approximate these guys at? So approximately, where is that guy going? 1.8, maybe? And for the quartile 3 on that? 1.7, Maddie, okay? And then quartile 3. Well, it's a little bit to the right of this, so I would say what, maybe 2.85? We're just kind of throwing numbers. Yeah, that's kind of what I was thinking, Maddie, somewhere in that 2.8 range. And then on the set here, what do you think quartile 1 and quartile 3 might be? Maybe 1.25. And this guy here, I don't know, 2.25 maybe, first quarter of between 2 and 3. All right, so what is this telling us in terms of infants who are diagnosed with severe idiopathic respiratory distress when we're looking at just the birth weights? Between, yeah, lower birth weight. Anything else? Okay, let's see what the example is talking about. I'm gonna leave my writing on for a minute, which I know will make the paragraph a bit hard to read. But they're saying basically when we're comparing the two groups, the box plot reveals that the birth weights of the infants that have died appear to be overall smaller than the birth weights of the survivors. In fact, we can see that the median birth weight of infants who survived is about the same as the third quartile. So yeah, we're kind of talking about the third quartile here, comparing that to the median birth of the infants that survived, right? So you can see these guys were not too far off from each other, which is a significant difference, right? Because quartile 3 is the 75th percentile, whereas median is the 50th percentile. So there's a good 25% of birth weights in there, right? That we are kind of comparing. Similarly, they are saying we can see that the 25th percentile of the survivors, which would be this value over here, kind of corresponds with the median or the 50th percentile for the birth weights for the infants that did not survive. So you can again kind of see that we are saying that over 75% of the survivors had a birth weight which is larger than the median birth weight for those infants that did not. survive. And I think that's a significant difference that we are seeing here between, what that syndrome can have an effect, right? And, of course, when it's a newborn, they don't have that kind of fighting abilities because their immune system is still building. And so once we kind of get into those lower birth weights, it is definitely something to be concerned about. And this is just a good way to just look at the data without having to look at a table, right? They did not give us table. They did not tell us how many were in the study, what our sample size was. And that's kind of where, guys, that visual representation becomes very, very crucial because we have no idea how many infants were in this study. We have no idea what their birth weights were. All we have is a summary, right? We know the minimum, we know the maximum, we know quartile 1, quartile 2, quartile 3. So it's very essential that, when we are representing our data, we needed to make sure when we're talking about birth weights, we are talking about what was the unit of measurement used. Same thing that we did in this example. We were talking about waiting times or service times that it takes. So it was crucial to mention what unit of measurement was used. And of course, that was minutes here. So remember how when we were talking about histograms last week, I told you guys, make sure you have labels on your X and Y axis, you have a title on your graph. So those are the kind of things that are important because we're not always given the raw data to look at. And so looking at the graph, it should be descriptive enough that we can gather enough information that is needed, right? Because remember how we were talking about biases in that first section where we were talking about intentionally or unintentionally, we could be creating a bias. And, obviously we don't want to do that by not having enough information shared, basically, I guess is what I'm trying to say. All right, so again, you can see we did this as a comparison. The second half of this paragraph is basically talking about similarly looking at the maximum value for the birth weights for infants that died compared to the survivors. You will again see that over 25% of the survivors had a birth weight which was higher. So you remember this is going from quartile 3 to the maximum. So that's 25% of infants who fall under that category. So you can see they had a birth weight which is higher than the maximum value that you are seeing for the infants who did not survive. So they're basically saying the box plot gives us a quick and informal, but a quick way to determine the birth weights linked with this syndrome. Alrighty, guys, so that was the last part of our box plots. Now, this is kind of where we're building up for section 3.6 and z-scores. Even though technically z-scores is used as a calculation for talking about spread or dispersion, you will see this is going to be a crucial measurement or calculation that we do when we talk about normal or nearly normal distributions. I prefer the word approximately normal, but your textbook is using nearly normal. So have you heard the saying that you can't compare apples and oranges? Oh, good Lord. Yes, I'm sure you have. So this is kind of the idea where normal distribution really comes in handy because, a lot of times you could be comparing, let's say we did comparing the height of people who identify as male, compare that with the height of people who identify as female. Now, yes, we are talking about height, so it may not be completely like apples and oranges, but we do know there's a distinct height difference, right? When you look at averages for males, compare that with averages for females. So a lot of times using like a standardized calculation might be a better way to consider, on an average, are men taller than women? Because that's kind of the general perception we have. So it could also be something like, if we're comparing people from the Scandinavian countries, right? Norway, Finland, we know they are known to be much, much taller, both men and women. But if you compare somebody from like Asia, right? China, India, we're short people. Let's own the fact we're short people. So there's going to be a big distinct difference between height averages, right? So if we can do a standardized calculation, then it kind of evens the plane, right? And it makes it easier to do a comparison of, on an average, how tall are the people or what's the difference between the heights and those kind of things. So that's kind of where we're talking about using a standardized measure might be essential or helpful than, like two quantities which may not be able to be compared. So here we're using what we call a standard score as the z-score. Z-score, this is a method commonly used where you have a unimodal and symmetric distribution. So think about, we talk about the bell curve, right? So your bell curve is going to be unimodal and approximately symmetric. This is my attempt at a bell curve. Not too bad. Thank you. So unimodal, approximately symmetric, which is where the term of normal or approximately normal distribution comes in. And again, I don't really like nearly, but it's okay. Z-scores may be used with any data, but if your distribution is skewed, then that actually also tells you that your Z-scores will be skewed also. And that's kind of why you will see a lot of times when we're talking about the normal shaped curve or the bell-shaped curve, we are kind of looking at that symmetric distribution. So calculating Z-score is pretty straightforward. Basically, we want to know how far away from the mean is your data value. So we take our data value, as you can see in the box at the bottom. So we take the data value, we subtract the mean from it, and then you take that difference and divide it by the standard deviation. So it tells us on an average, how far away from the mean is your data value going to be? So we're basically saying the z-score of a data value is the number of standard deviations it is away from the mean. Trying to see if I can simplify that before we get into a calculation. So in a unimodal or symmetric distribution, remember your mean falls right in the center, which again, if it is symmetric, then we know the mean and median will have the same value or at least approximately equal value, right? Standard deviation tells you on an average, how far away is your data from the mean or from the center. So a lot of times, if your standard deviation came out to be 2.37 or whatever, depending on the set you are looking at, we would basically then say when you're calculating the z-score, we want to know how many standard deviations are you away from the mean? Are you one full standard deviation away, or are you anything in between? So you could be half a standard deviation away, you could be 0.75, or you could even be more than 1, 2, or 3 standard deviations away. So we kind of use standard deviation as the basis of how far away from the mean you are, instead of just like, it's 5 units away from the mean, because that would just be like you were calculating a range. But z-score, because we want to standardize our calculation, we base it on standard deviation instead of just, 25, my data value is 10 units away from the mean, which wouldn't really tell us anything when we're looking at, like I was saying, height of men compared to height of women. 10 inches could be a big deal for men or women, or like I said, Scandinavians compared to Asian. So in that case, just using raw data is not going to be enough. That's why we need to do the z-score, which is based on that standard deviation. So start by calculating the subtraction first, do the difference first, and then you do the division. So let's take a look at some of this here. So they're saying, okay, if a data value is above the mean, then your z-score will be positive. And we had talked about this a little bit when we were doing deviation calculations, that, if the data value was larger than the mean, you would get a positive deviation. If you had a data value less than the mean, you would get a negative deviation. So that kind of applies here also. So if the data value is above the mean, your z-score will be positive. If the data value is below the mean, z-score will be negative. So basically we're saying if your data value is exactly 1 standard deviation above the mean, then your z-score should come out to be positive 1. If it's going to be 2.5 standard deviations below the mean, then your z-score should come out to be negative 2.5. And then they are saying the unit of your z-scores are actually standard deviations. They are not what your raw data is based on. Is again, remember, we're not really comparing the raw data by itself. We're doing it in terms of the standard deviation. So the unit of measurement technically for z-scores is how many standard deviations are you away from the mean. If it's positive, that means you're above the mean. If the standard deviation is negative, you are below the mean. So that's kind of what the positive and negative in the z-score would tell you, is where it falls. They are also saying we can use z-scores to determine the relative unusualness of a data value with respect to its distribution. So basically, you can compare two unlike items. And I think that's the important part here is, those apples and oranges that they were talking about. You can compare two unlike items by using this idea of a z-score. So they're saying basically in statistics, it is convention to say that a data value is unusual if it is more than 2 standard deviations away from the mean, and that can be above or below the mean. It does not matter. So if you have a z-score of larger than +2 or smaller than -2, we would say it's an unusual occurrence. This doesn't happen often, okay? So let's take a look at example here, guys. Okay. So oranges at a local grocery store have a mean diameter of 5.8 inches and a standard deviation of 1.2 inches. That's for oranges. Apples, on the other hand, have a mean diameter of 4.2 inches and a standard deviation of 0.6 inches. So just by looking at the mean diameter between oranges and apples, which one is the larger fruit? Between oranges and apples, which one is the larger fruit based on its mean? Yeah, Samuel, very nice. It will be oranges because they have a higher mean of 5.8 inches compared to apples of 4.2 inches. And then look at the standard deviation on both of those. Now we have a standard deviation of 1.2 for oranges. And remember how I was telling you guys that the larger the standard deviation, that means it tells us the more spread out our data is, the smaller the standard deviation, that means more close to the mean you are. And you will see, of course, with apples, we have a smaller standard deviation. So they're basically saying Ali closes their eyes and selects an apple and an orange. When they look at both pieces of fruit, they seem small. If the orange has a diameter of 4.2 inches and the apple has a diameter of 3.5 inches, which is smaller relative to their respective piles of fruit? So this is where the z-score basically comes in. So on the orange, they're saying the fruit that Ali picked up, the orange had a diameter of 4.2 inches. So you can see that's our data value. Subtract the mean from it and then divide by the standard deviation. So you can see for an orange, it's coming out to be negative 1.33 standard deviation. So we're basically saying it's actually smaller than what the normal, 5.8. Is that what we had? Yeah, 5.8 was the mean for that. When we do the apple calculation for the apple, the diameter for the fruit that Ali picked up was 3.5 inches. So that's 3.5 minus its mean and divided by the standard deviation. So you can see this guy is coming out to be negative 1.17. So both fruits, because you have a negative z-score, is telling us they are smaller than the mean, than the average, right? What we have here. But when you compare the two, you will see that apple has a smaller standard deviation value than the orange, right? So by this sense, we would say that the orange is 1.33 standard deviations below its mean and the apple is 1.17 standard deviation. So since the orange has a larger number, that guy is more smaller than the other fruits in the pile of the oranges. So the orange relatively is much more smaller than the apple is because the apple z-score was higher than the z-score for the oranges. Because, you know, again, you can only compare orange to the pile of oranges, right? You can compare the apple to the pile of apples. So based on that, we would say from the average, the orange that Ali picked up was much smaller than the pile that was in front of him, and the apple was not as small as the other guys in the pile. And this is honestly where a comparison like this would make sense, because you do want to have, you know, two items to compare to see which one relatively would be smaller than the other. So basically they're saying, we can also see from the z-scores that neither fruit has an unusually small diameter, since they were both within two standard deviations, right? We didn't have a number smaller than -2 or a number larger than +2. So we did not hit that unusual category. So they were still within the usual limits because we were not two standard deviations below or above the mean. To use your spreadsheet, to calculate the z-score, you have a built-in function called standardize. So here you can see the argument is we put the data value, the mean, and the standard deviation, right? The three numbers you need to calculate your z-score. So those would be the function we would use on our Google Sheets or Microsoft Excel, whichever program you're using. So you can see for the apple example, the one Ali picked was 4.2 inches. No, this should be orange. Because the orange was at 5.8, this guy should be out. So yeah, orange he picked up was 4.2 inches. The average for that, the mean was 5.8, and the standard deviation was 1.2. So his, or their, I guess they used their orange came out to be -1.33 below the mean in terms of standard deviation. And then for the apple, the one they picked up was 3.5 inches. The mean was 4.2 and the standard deviation was 0.6. So their apple came out to be -1.17 standard deviations below the mean. All right, let's get rid of this guy. Before we look at the solution, let's take a look at the question. So this guy's talking about the mean weight of men over the age of 20. So the mean weight of men over the age of 20 is 195.7 pounds, with a standard deviation of 29.8 pounds. The mean weight of domestic cats is 8.6 pounds, and their standard deviation is 1.2 pounds. They're saying the standard deviation of men's weight is estimated. The cat's mean weight is based on ideal cat weight, and the standard deviation is approximate. Okay, so at his peak, Andre the Giant was, 7'4" tall, French professional wrestler, and he weighed at about 520 pounds. When Georgia the cat was at his peak, he weighed 24 pounds. Who was more giant, the man or the cat? So this is kind of, it may sound like an absurd example, but I think it's perfect, because remember how we talked about you can take two unlike quantities and compare them. And nothing gets more unlike than a cat versus one of the tallest, heaviest man that was known. So yeah, in this case, think about this. So we are basically saying Andre the Giant weighed at 520 pounds. They're telling us the average weight of men, which is the mean, is 195.7, and then you would divide that by the standard deviation, which is 29.8. Whereas, what was the cat called? Georgie? You know the spell. Sorry. Where was Georgie at? 24 pounds? And then they're telling us for mean weight of domestic cats is at 8.6, and their standard deviation is 1.2 pounds. So obviously we're dealing with very different averages and standard deviations over here. But when we put this through our calculation, now in both cases, you will see the man and the cat were heavier than the average, right? So they're quite a bit above their average because cats, we are saying, are at a mean of 8.6. So that's 24, which is 3 times the average weight, isn't it? And Andre at 195, even if we said 200 was the average, that's about 2.5 times more than the average person, right? So you can see there's a pretty big difference in the weights of these unusual representations of their individual category. So look at their Z-score when we go ahead and you know, you can do it by hand or you can use technology. Either way, you can see that Z-score is coming out to be 10.88 for Andre and 12.83 for Georgie the cat. Now, would we have guessed in their own category, Georgie would be the higher standard deviation over there? I mean, it's a cat. How much heavy can a cat get? But I guess it's the same thing that applies for humans also, right? I mean, how much heavy can we get? I mean, it's possible. I had a friend whose dog was the tiniest, but I swear he looked like a boss. Because all he did was eat human food all day, every day. Like it did not eat dog food. It did not know what dog food was. It lived, and it did not have a healthy life. I'll tell you that. It had a pretty miserable life because short stature dog looked like a box and could barely crawl across, you know, we basically carried him everywhere. I think he would have known Georgie because that is not nice when you are 12.83. I mean, we were talking about unusual being at 2 standard deviations above or below the mean. That's 10.88, almost 11, and that's 12.83, almost 13 standard deviations away from the mean. So both categories in their own selves is unusual, right? But like I said, the cat kind of surpasses the giant man for its own category, just because you can see it came up with a higher standard deviation. And again, you can see they're just showing you how to do the calculation if you were using a spreadsheet. So since both z-scores are greater than 2 standard deviations, we know they are extremely unusual, but Georgie's weight is much larger than Andre the giant, which is just astounding to me. I've never seen Georgie the cat, but I've had different examples where, you know, people have talked about it. So what's the average for their category? Like, because, you know, again, it differs from species to species also.
It's a large species or breed, whatever.
So their breed will run higher. So see, I think he may not be.
That's why I was like, you know what, that cat may not even be that fat, because my cat's not, he's not. Some cats get big. No, my cat, he's just big. He's just a big cat. Like he's like
Like they're
this
not
small.
specifically fat,
And you
but
stretch
like,
him out.
what breed is he?
He's a Norwegian.
Maybe he has some of those Scandinavian genes like people. I'm telling you, some of these people are tall. I don't know if I have told you, my roommate in college was 6'2". I was looking at the sky when I would talk to him. Because, you know, here I am 5'3", and I will stick to that, people. I am 5'3". And here she is like 6'2", and I was like, okay, you get all the top cabinets in the kitchen. I get all the bottom ones. It worked out great for us. All right, so we've done the 5-number summary, the IQR, so I don't want to repeat that example. Okay. Kind of hoping you would just do something with C-scores. I think this is it. Looking to see if we can also do a comparison between two groups. I think this might be it. We're looking at running time of movies. So yeah, let's pick one of those examples. So number 20 here is talking about the mean running time for comedy movies is 139 minutes with a standard deviation of 39.7, but for action movies, they are saying the running time is, the mean running time is 159 minutes with a standard deviation of 26.2. So they're saying a recent comedy movie had a running time of 102 minutes, so that was a comedy. And for an action movie, the running time is 129. So they want to know which movie is shorter compared to other movies in the same genre, and they want us to do this using obviously z-scores as a comparison. So let's take this and actually, so I can show you how to use that standardized function in a spreadsheet. Let's copy this over. So, all right, there we go. Okay, so we are talking about two categories over here, comedy and action movies. Okay, so they're telling us the mean for comedy was 139, and this is in minutes. For the action, it was 159, so they're running longer a little bit. Okay, the standard deviation for comedy was 39.7 minutes, and for action was 26.2. Okay, so current recent comedy movie, so this is our recent data values. For the comedy, they are saying the running time was 102 minutes. For the action movie, it was 129 minutes. They're both below their average, right? Because for comedy, the average is 139. This movie was only 102 minutes. For action, the average or the mean is 159, and the movie in the recent one was 129. So let's do the z-score calculation. So remember, you're using the standardized function. So you can see that popped up in our so the first one is going to be the data value. So that's actually going to be the current running time of the movie, which is 102, comma, then you do the mean. So for the comedy, the mean was 139, and then the standard deviation, and you can see that was 39.7. So that'll help us calculate the mean. Sorry, the z-score, and it should be negative, right? Because the time was less than the mean for the running time. So we should end up with a negative. And remember, the convention is 2 decimal places more than your data, which in this case would be in whole minutes. So we can round this to, 2 decimal places. Same thing for the action movies. We are doing standardized. Did you use the right cells? So the data should be 129. The mean should be 159. Standard deviation should be 26.2. So it looks like it did use the correct values in there. So hit enter, round it to 2 decimal places as well. So for each of their own categories, your question was, which movie is shorter compared to the movie in the same genre? Is the comedy shorter, or is the action movie shorter compared to, its category, its genre? So the comedy movie has a z-score of negative 0.93. The action movie has a z-score of negative 1.15. So the action movie has a longer z-score or a larger z-score compared to the comedy. So how does that translate to our question? Which movie is shorter compared to the movies in its genre? So remember, the larger the standard deviation, the farther away from the mean you are. The smaller the standard deviation or z-score, same logic, the closer to the mean you are. Very good, yes, because that has the larger z-score. So the action movie compared to its average is actually quite a bit shorter than what it would normally be for its genre. So yeah, very good. Action, ooh, there's no G in there. Action movie is shorter than its genre. Perfect, very nice. Okay. Yes, let's do this one. Poe, the Clydesdale horse, has a world record breaking height of 20.2 hands. All Clydesdale horses have a mean height of 16.5 hands and a standard deviation of 1.85 hands. The last Great Dane to hold the world record for dog height was Gibson, who was 107 centimeters tall. Great Danes have a mean height of 81 centimeters, standard deviation of 13. Which animal is taller compared to their respective breed? So one thing that should stand out to you is, of course, we're talking about two completely different breeds of animals, but we measure horses in hands, right? Whereas dog here is being measured in centimeters. So even two different measurement units that are coming into play. So you can again see it's not just that, we were talking about different animals, but we're also talking about a different measurement unit being used here. So again, a great place to see how a standardized calculation like this guy comes into play, the z-score. So all Clydesdale, which I think Clydesdale are beautiful horses. Okay, so their mean is 16.5, standard deviation is 1.85, and then Great Danes, which are also beautiful dogs. And let's see, they have a mean height of 81 centimeters and a standard deviation of 13 centimeters. Okay, so same thing, which animal is actually taller compared to their respective breed? So this one is wanting to know taller than usual, I guess. All right, so you should be able to see the whole problem now. So we've got this will use the name. So we've got Poe, Clydesdale, and we've got Gibson. The Great Dane. Okay, so their mean, standard deviation, and then of course the current height for the animal itself. So the mean for Clydesdales was 16.5 hands. The standard deviation from there was 1.85, and then Poe himself was 20.2, which we can see is higher than the average, right? The mean value. For Great Danes, we are saying the mean height was 81 centimeters. Standard deviation was 13 centimeters, and Gibson himself was 107, which is. All right, so this is measured in centimeters. And Clydesdale horses was in terms of hands.
They don't have that many hands.
They don't. Do they have any hands?
They are hands,
Yeah.
kind of.
Alrighty. So can you tell me what the z-score for each category is?
I got two today.
Exactly 2? No decimal?
Zero.
Okay, so that would be the function standardize. Okay, so Poe is at 20.2 hands. The mean was 16.5 and standard deviation was 1.85. Oh, look at that. So technically, since the height is given to us in one decimal place, we should actually have 3 decimal places. So even though it's 000, I'm going to show you so you remember that it should be 2 decimal places more than the raw data value.
Why?
That's the rule. Yeah. And again, you can see this guy. Did we use the right numbers? So data was 107, mean was 81, and standard deviation. Okay, so this guy was whole number, so your z-score should have 2 decimal places on it, so 2.00. But yeah, very good. So what does that tell us? Which animal is taller compared to their respective breed? Yeah, I mean, they're both tall compared to their breeds because we are at that unusual mark, right? We're at 2 standard deviations above or below, in this case, above the mean. So it's unusual because among Great Danes, Gibson was obviously at a height which was not usually what we see for Great Danes. And then same thing for Clydesdales. Poe was unusually taller than what his breed mates would be like. So actually neither one of them or both of them, however you want to look at it, would be taller. So I would say both. Both are taller compared to their respective breeds. Bless you. All right, guys, questions on this last part here with the z-scores and using that as a comparison tool for basically unlike quantities that could be compared together. Everybody okay? Yeah? Zoom, I'm seeing something pop up on chat. No questions for the z-scores from Samuel. Okay, did anybody else on Zoom or in the classroom have questions on this section? Because this was the last part from section 3.4. Don't want you guys to feel like I'm kind of rushing you into, the next section, but Maddie, no questions. Okay, no problem. If you do, sure. So yeah, like I was telling you, section 3.5 is review, so we're not skipping it over. For whatever reason, the authors felt like, oh, 3.6 may be an optional topic, we're gonna put it at the end.
Why did they do it?
I don't know, I think it's kind of silly because I think in any study of statistics, we should at least talk about normal distribution. Now, there are other types of distributions, there's binomial, T distribution and all of those. But I can understand we're just doing this as an introduction, but I think normal distribution should still be in there. So at Ames, we definitely consider teaching normal distribution. So for us, this is not an optional topic, even though your textbook is kind of treating it that way. All right, guys, so we will be coming back and using z-scores, as you can see, with the normal distribution also, but we'll, obviously build up on that. And then I think it was section 3.1 or maybe 3.2, because 3.1 was, I think, just about using spreadsheets. Remember, we had talked about confidence intervals and margin of error there, so we'll actually be coming and talking a little bit more in depth of that also. So when we are, and I've kind of already mentioned this to you guys, when we are talking about the normal distribution, this is where, we talk about the unimodal or the symmetric shape of a distribution. So here we're saying there is a pattern or a shape that comes up frequently when we are graphing data, and that is what we call as the normal distribution, or sometimes we call it the bell curve. So when we take measurements like length of newborn babies or weights of potato chip bags on an assembly line, this is where you will normally see that, we will have that one peak kind of in the center for our mean or median. So that's where your average would fall. And then basically they're saying there's usually more measurements near the mean. So they will be kind of gathered in that center of your distribution, and fewer as you kind of get on each side, or, like the tail end of your bell-shaped curve over here. So this shape is kind of what we're talking in terms of a bell shape. Now you will see the height of those bars are not even, right, in the histogram, because there's a little bit of, there we go. So, like you can see from the center where you have the tallest bar to its left and right, they're not evenly spread out. But in general, you can see how they have that overlying bell-shaped curve, right? So we're saying this is approximately a symmetric distribution. So remember, it does not have to be like a perfectly symmetric histogram. As long as we can have that approximate normal distribution or that approximate bell curve, we can use these calculations that we're getting ready to look at. So the shape should be unimodal. It should be symmetric, with smaller and larger values getting less and less common the farther away from the mean you go. And then we're also talking about when we take samples from a population, we may not get an exact normal distribution, excuse me, but it will be close to that. We call this approximately normal or nearly normal distribution. The curve drawn over the histogram shows that this is, again, that approximate normal shape over here. So remember how when we talk about symmetry, the mean and median should be approximately equal, right? They should be close. So what we actually say for a normal distribution is mean, median, and mode can actually be approximately equal to each other. So even your mode will fall right there. So that's going to be usually in the center. So right here is where your average would be. So this is where your mean, which would be approximately equal to your median, which will be approximately equal to the mode. So that will be right in the center of your distribution or your bell-shaped curve. And we actually often, when we are talking about the mean, we use the Greek letter mu. And it kind of looks like a U with tail at both ends. At least that's how I draw it. For standard deviation, when we're talking about in a normal distribution, so for the standard deviation, we would usually use the, again, lowercase Greek letter sigma. I don't know, what is that, 6 sleeping on its side kind of thing, So Greek letter mu for representing the mean and Greek letter sigma for representing the standard deviations. A lot of times in certain textbooks, you may see they may use, and we kind of talked about this in the last section, we may use small letter s, capital letter S for standard deviation, but usually when it comes to normal distribution, we kind of stick with those Greek letters. So just a notational thing. Alrighty. So properties of a normal distribution. So regardless of the data values, the normal distribution should have these properties here. So it should be unimodal. It should be symmetric around the center. Your mean, median, and mode, all three of them have to be approximately the same value. And due to the symmetry, because a bell-shaped curve will have symmetry, due to the symmetry, approximately 50% of the data should be below the mean and 50% of the data should be above the mean. So you can see in this image over here, we've got, those labels. So you can see how you have mean, median, mode, all in the center of the bell-shaped curve. You have 50% below and 50% above. That symmetry is very, very crucial, guys. And I know it's kind of hard to see in this graph, just the way they have it presented, but the horizontal axis should not be touching the tail of the bell-shaped curve. So there should actually be a gap between the horizontal axis and the tail of that bell-shaped curve, because it's never going to reach like 0 for it to touch the horizontal axis. So like I said, it's kind of hard to see that there, but there is a tiny bit of gap between the tail ends and the horizontal axis. Alrighty. Let's make this guy smaller. Also, they are telling us almost all of the area under that normal curve is within 3 standard deviations of your mean, and then they are also saying data within 2 standard deviations is considered typical or usual. Anything beyond 2 standard deviations, as we talked about, will be considered unusual. So anything that you would have beyond 3 standard deviations would be a very, very rare case. Okay, so those are some of the properties that we are. So we're gonna build up on this, guys. We'll get into the empirical rule next time and then see how normal distribution can be used in our calculations, okay? So like I said, I'll go ahead and open up the 3.6 homework now that we're officially talking about it. But please make sure that you guys are caught up on as much homework as you can. And just remember, if you are going to tutoring, you actually need to be sitting there and working for homework, and you're not just sitting there, like I said, with a timer on your phone and just waiting for that to count down. You have to be working with a tutor to count as your time, okay? All right, guys, if you have any questions, please stay back, and if not, I will see you on Thursday. And again, if you are on campus this evening, please stop by for trick, track, treat, whatever that thing is.
Or treat track.
Thank you. Trick or